the problem. Let's redo. And there's this nicely decomposed again already. And let's see this curve, and I sketched it here for you. And orientation, I think I remember when I tried negative pi, it was over here. Do you remember anything about this curve you might have sketched yesterday? It starts from there, is that right? Yeah. And then end up at there, going around. And this time I gave you the answer, 6 pi I, and you're supposed to explain that. So here's my idea. All right, if you start there, kind of, it involves logarithmic cuts in 1 and negative 1 is here and there. They're all going across in here, right? So I looked at, here's a negative 3. I think I labeled that B. And you can see that goes down this direction. Is that right? That's the orientation, negative 3. It's here, going out like that. And let's follow it. That was actually tricky. You'll end up in here, right? So we're going to add there, and I'm going to call that A. That's almost like near negative 4, right? It's not exactly negative 4, negative 4. So go around like that, and it definitely go around that branch cut. Never touch the branch cut. There's no branch cut in integrate function, but if you think about antiderivative, you know in your mind how there's a branch cut. I'm going across it or not, but here there's no branch cut going across here, right? And until you're coming back here, right? So doesn't it almost look like one rotation? So I thought about, I'm going to close up the rotation. So by introducing this curve, gamma 1. Gamma 1 isn't there, but I'm going to close it up. Doesn't that look like a simple closed curve now? Then what theorem applies? Cauchy-Gauss. We have one loop and two singularity, right? Then you can calculate this, right? By replacing simple two loops around there. This is wobbly, but you can replace it with the two small loops around two singularity, 1 and negative 1, correct? So we know how to answer this guy. Okay, so I'm going to call that one C1 and remaining part gamma 1. I close it up all together. I'm going to call C1 bar. How about that? This notation okay? C1 is the original part. I close it up and then C1 bar. All right, now I'm starting at negative 4 here, and maybe I'm going to, we have time. So I'll do it in here, not copying. So we were here A, and then we're continuing down that way. You agree? There, down that way. And you're going around. We arrive in here and far on to the left in here. So I'm going to call that one C. It's arriving in that fashion. Agree? Okay? So our singularity is all that side. So I'm going to close it up with second curve, right? We arrived at here, so we have to go backward like this. Agree? Yeah. So that's a gamma 2. So there's a C2 curve, and there's a gamma 2. I'm going to call that C2 bar as a C2 plus gamma 2. So that it becomes a closed loop. And it picks up another Cauchy-Gauss theorem that gives you two circles, right? Exact same value repeated. You just have to think about, what about this gamma 1 and gamma 2? It's going to do. So last bit, how does that happen here? We started here now, right? Let's see. And that goes around in that fashion, and of course it's going to come back to the original B. Right? There's a B. B here, arriving in that fashion. Okay, so that's curve C3. And what's gamma 1? Which direction is gamma 1? To the right or left? Right. And here's a gamma 3. And C3 bar is going to be C3 plus gamma 3. This plus means an integration behavior. It's actually the union. Okay? So what we want to know is that C1, well, what do you think about C1 bar, C2 bar, C3 bar? Who can calculate that? C1 bar is a simple closed curve, is that right? We have this funny flat part. So what do you pick up? There are two loops, two singularity inside, right? So 2 pi I, 2 pi I? right? 2 pi I, 2 pi I. And did I make a mistake? This picks up two singularities there, right? Isn't that supposed to be 12 pi I then? Right? There's 1 and -1. So I think that was a 12 pi I. Sorry about that. So this picks up 2 pi I, right? 4 pi I, because one singularity picks up 2 pi I, the other one picks up another 2 pi I, right? And this one's the same curve. Cauchy-Gaussat says 4 pi I again, and 4 pi I, right? They're all the same. So it's 12 pi I. Sorry about that. There are two singularities there, right? 1 and -1, and a -1. Okay. What remains here? So that's not what we want. We want is C1 plus CO2 plus C3, right? That's what we want. That's the original curve. So let me separate it. 12 pi is going to be C1 plus C2 plus C3, right? But what should be added here? The additional thing we throw in. Gamma 1 plus gamma 2 plus gamma 3, right? Make sense? So let's look at it. Gamma 1 is about this point ABC, right? Gamma 1 and gamma 2 and gamma 3 are going back and forth around ABC. So where's gamma 1? Gamma 1 is from A to B. The gamma 1. What about gamma 2? Gamma 2 is going from like this. That's gamma 2, right? C to A, all the way C to A, right? C to A. How about gamma 3? Going this way, gamma 3, right? Okay. So what do you see? Cancel. Gamma 1, gamma 3, and gamma 2 backward. Cancel. So that's the same as this one, right? So that 12 pi I was the correct answer. I didn't do this on purpose. I just made a mistake, and they might have caused a lot of pain. So I'll give you points to that too. But let's think about this one. All right, here in the general discussion, I'm here, and let's say it's loop around 2014 times. Okay, 2014 times, and there are singularities here and there, right? Turns out, if they're going across like this, this singularity counts, and this singularity counts, that singularity doesn't count because branch cut goes this way to the left. But if there's nothing is going in between these two singularities, they're all going across it here, then you go first time you cross it here, let's say P1. Next time you go across it here, you can imagine the fashion this when it's appearing is erratic. There's no pattern, right? It could appear here, P3, then it could appear over there in P4. The crossings, right, as you go around. Now, then this is the vectors. P1, what is the next vector in here? It's going to P2. Maybe it's backward, but you can backward later. We're going to P2. P2 later, P3, right? P3 later, P4. These are the connections. These are the one-dimensional vectors. So it's like one vector followed by the heading. From the tail to the new vector. Remember this thing? Vector, tail to the vector, this two-dimensional vector. These are the directional vectors, right? If you add them all up, this vector v1 plus v2 and v3 and b4, this directional vector add up becomes a position vector. And what is the resulting position vector? Is the starting point to the end point. Remember that part? Yeah. So the same thing. If you keep adding P1, P2, P3, these are all directional vector chasing each other, right? What is the sum of the whole thing? Beginning and end point, right? But you're supposed to come back to P1, remember? So therefore, they all cancel. And I explained why they cancel in however complicated fashion, right? It always cancel. But this is backward. If you look at actually here, the gamma doesn't go from first position to second position. It's going backwards, right? But it's all backwards in the same fashion. So negating the whole calculation still gives you a zero vector. So that actually is the final part of the proof. So if you kind of go around, whatever the definition was, this kind of intuitive notion of what do we mean by just going around, there's no particular distinguished point. It's all about around the singularities. And then it is about number of looping around is a 2 pi I times winding number multiplied is going to be always the answer. And I hope this actually explains why that is so. Does that make sense? All right. I'll let you go.